Hi, I'm Matthias Beck. I am one of the authors of Computing that Continues Discretely. And in this video, we'll start chapter 10. We'll introduce h-polynomials of simplicial polytopes and of triangulations. Let me remind you about the Dehn-Somerville equations. So we discussed them in chapter 5 for simple polytopes. A simple polytope is one where each vertex sees exactly d edges, if my polytope has dimension d. And the Dehn-Somerville equations for simple polytopes, you see here, theorem 5.1. For us, this was a corollary of sort of an Erhard polynomial setup. And the dual version, and we briefly talked about this in the videos for chapter 5, is a simplicial polytope. So a simplicial polytope has facets that are all simplices. And there is a version of Dehn-Somerville for simplicial polytopes, and it's given in exercise 5.9. Namely, if your polytope has dimension d, you have these relations among the phase numbers. So this was just a review. Let me rephrase the Dehn-Somerville equation for simplicial polytopes using what's called h-polynomials. So my setup is that you have a simplicial polytope and the dimension is d. Then again, here are the Dehn-Somerville equation. What we'll do now is we rewrite the Dehn-Somerville equation in a different form, and to that extent we define the h-polynomial that you see on the right here. The phase numbers are the ingredients of these polynomials. If you want to doing a change of basis here in a space of polynomials. This seems a bit out of the blue, but in this video I will give you two good reasons for this definition. One of them, I claim, this theorem 10.1 that you see here is a reformulation of the Dehn-Somerville relations for simplicial polytopes. And it says, if you have a simplicial polytope, then the h-polynomial that you see on the right is palindromic. Its coefficients are symmetric, whether you read them from right to left or left to right. But this is not hard to prove once you have the Dehn-Somerville relations. And I invite you to compute some examples. So for example, if your polytope is a simplex, the h-polynomial has a very easy form. The reason why I wanted to review the Dehn-Somerville relations for simplicial polytopes is because I want to talk about triangulations. So we'll fix a triangulation T. Of a polytope. So just to remind you, a triangulation is a collection of simplices that intersect nicely and whose union is all of P. But what I'm really interested in for now are boundary triangulations. So you can think of these as a triangulation of the boundary of a polytope, or you can think of somebody hands you a triangulation of a polytope, and then you restrict yourself to those simplices in the triangulation that are contained in the boundary of P. And then for boundary triangulations, I can again compute an h-polynomial. And in fact, I can use exactly the definition that I used for polytopes. If you think of a boundary triangulation, that's a collection of simplices. I can compute the number of faces in each dimension. And because my simplices live in a boundary, the top dimension is d minus 1. And if you look at my definition of the h-polynomial of a polytope, we're recording the face numbers of dimension up to d minus 1. Yeah, so I will literally repeat the definition that you see on top here for polytopes and compute the h-polynomial of a triangulation the same way. It's just my face numbers come from the simplices. The philosophy is even closer if my polytope up on top is simplicial, because now all of your faces, non-trivial faces of my polytope, are simplices. And so I hope this really makes sense to just repeat the definition of the h-polynomial. Anyway, as you might expect, there's a Dehn-Somerville theorem now for boundary triangulations, and it's the same theorem. The h-polynomial of a boundary triangulation is palindromic. We're stating this theorem here for the following construction. You start with a regular triangulation. We introduced those in chapter 3. And then restrict yourself to the boundary that gives you a boundary triangulation. And then compute the h-polynomial, and this polynomial will be palindromic. Let me give you a picture that gives you a starting point for a proof of theorem 10.2 if you have theorem 10.1. Namely, what I do is I construct my regular triangulation, and what you can see in this picture, I'm adding an additional point sort of at a height that's larger than the heights of the lifted vertices of my construction for the regular triangulation. And then I'm intersecting the resulting d plus 1 dimensional polytope at a height just below this extra point. And so I invite you to see that what we get when we intersect the lifted polytope at this height, we will see a picture of the boundary triangulation as a simplicial polytope. And because simplicial polytopes satisfy the Dehn-Somerville relation, so will now the face numbers of this boundary triangulation. I promised you a second reason why h-polynomials, the way we defined them, are a nice construct. And that is now, again, I'm starting with a polytope P. Of dimension d, and T is now any triangulation. So this is not a boundary triangulation anymore, but a full triangulation. So now let me define another h-polynomial for this triangulation. So you might notice that I'm now going all the way up to d-dimensional faces because my triangulation is a full triangulation. So I need to keep track of, for example, the number of full d-dimensional simplices in the triangulation. Anyway, this is sort of the natural definition for the h-polynomial of a triangulation. Let me remark that Dehn-Somerville does not necessarily hold for this h-polynomial. So for Dehn-Somerville, I really need a boundary triangulation. At any rate, I wanted to go in a slightly different direction over here and assume that T is not just a triangulation, but a unimodular triangulation. So what does that mean? So it's a triangulation into unimodular simplices, and a unimodular simplex is is a simplex in d dimensions, let's say, where if I pick any vertex and compute the differences of the other vertex with this given vertex, then I have d resulting vectors, and my simplex is unimodular if they form a z basis of z to the d. The standard simplex, if you take the convex hull of the origin and the d unit vectors, is an example. And one way to think of unimodular simplices is to take the standard simplex and then consider a unimodular image of that. Anyway, so the theorem I wanted to show you is that if you now have an integral polytope that comes with a unimodular triangulation. So this is a triangulation into unimodular simplices that we just defined. Then this theorem 10.3 says that the Erhard series, which we know is a rational function with denominator 1 minus z to the d plus 1, has numerator equal to the h-polynomial of this triangulation. So this numerator for Erhard series in general we call h-star polynomial. So one way to rephrase this theorem is to say that the h-star polynomial of an integral polytope that comes with a unimodular triangulation is equal to the h-polynomial of this triangulation. This is sort of a cool theorem because what we're saying here is that you can compute the Erhard series in a purely combinatorial fashion. You can compute this object that really encodes the lattice point behavior of my polytope simply by counting phase numbers of this triangulation. It also says, by the way, that the h-polynomial is independent of which unimodular triangulation we choose. At any rate, there's another message here, and it says that unimodular triangulations are pretty special. This is another instance of where the two-dimensional picture is misleading. So I claim that any lattice polygon comes with a unimodular triangulation, but this is far from true for higher dimension. So from dimension 3 on, polytopes that admit a unimodular triangulation are quite special. Let me give you just a little bit of an idea of why this theorem is true. And that is, if you have a unimodular simplex, let me call this delta, of dimension d, then I claim, just like with the standard simplex, the Erhard series of delta is of a very simple form. It's 1 over 1 minus z to the d plus 1. So it's this one that allows us to compute the Erhard series of the polytope somehow by counting faces of the triangulation. After all, if you have a unimodular simplex, each face is again a unimodular simplex. This doesn't quite explain why the h-polynomial of the triangulation appears, but this is spelled out in detail in section 10.1. What we'll use here is we use Erhard-McDonald reciprocity to go to the interior of each unimodular simplex. And once you do this step and write the Erhard polynomial of a polytope as the sum of the Erhard polynomial of these relatively open unimodular simplices, you will see the h-polynomial of the triangulation appearing organically in the numerator of the Erhard series.